Today we'd like to go a little farther with our moving charges with magnetism unit. Remember, the goal of the unit is to get charges, specifically electrons, to move using a magnetic field. Remember, we cannot create a magnetic force if the charge and the magnet are at rest. You only get a magnetic force when the charge is in motion, and then you get a deflecting force created on the charge. The reason why is because when charges move, they create their own magnetic field. This magnetic field only exists when the charges are moving. We looked at how this field worked for wires, and then we used this when we create our railgun. Remember, with the railgun, we send electricity through a metal rail. That electricity creates a force, which is going to get this rail to accelerate. And we can create really high accelerations by having the right combination of currents and magnetic fields. This unit, however, we're going to be taking a step in a different direction, and instead of creating magnetic forces to move objects, we want to use the magnetic force to move charges. We want to induce currents in our circuits. We want to produce electrical current without needing things like batteries. We saw it all started by moving a metal rod through a magnetic field. We saw that it caused the electrons to move to the top of the rail and the positives to stay where they were. We then hooked this up to a system where we had stationary rails and we had electricity flow through our circuit and light up our light. We saw that if we moved the entire circuit, this wouldn't work. We then did a little lab where we pushed a metal bar along a series of rails to see how much voltage and current we produced. We varied things like the magnetic field, the rail separation, and the velocity. We saw that all three of these changes produced a direct proportional graph. So more magnetic field gave us more voltage and more current. We saw that a bigger rail separation produced more voltage and more current. We saw that a higher velocity gave us more voltage and more current. This is the formula that emerges from that lab. So the last thing we did was this lab, and I want you to realize this is the result of the lab. This thing here is called the electromotive force. It's just a fancy name for voltage. Voltage not created by chemical reactions, but by an actual force. That's why we call this the electromotive force. Okay, and the B is the magnetic field. Make sure you work in Tesla. The L is the rail separation. Make sure you work in meters. And V is the speed. Make sure you work in meters per second. All right, so we have rail separation, velocity, and magnetic field. Multiply them all together, and you get your voltage. It's called the electromotive force. Most times we don't really care about the voltage, but we need the voltage to figure out how much current is going to flow through our circuit. So you just use Ohm's law, but instead of using volts on top, you use electromotive force. It's the same thing. It just has a different source. Instead of being created by chemical reactions, it's being created by our magnetic field. Okay, what I want you to realize about this is it's not a free lunch. We think that if we push an object, that the object will continue to move. This is Newton's first law of motion. Objects in motion continue to move until some force acts on them. So we think that if we give this metal bar a push and we get electricity flowing and it lights up our light, that this is going to continue as long as the bar moves. And all of that is true. But what happens is, as electricity flows through the metal rod, it creates a current. And we learned before, if we use our left-hand rule, we put our thumb in the direction of the current our fingers in the direction of the field, you'll notice it creates a force on the bar that counteracts the velocity of the bar. It slows the bar down and stops it. It's kind of like an electrical magnetic friction. So it stops the bar from moving and it's going to shut the light off. So if we want to keep this light moving, we need a constant source of energy to counteract the force that is generated by way of Lenz's law. Lenz's law is always going to try to stop us from getting our free current. It's going to try and restore things to their original state, which was at rest. I want you to realize that this is a very impractical way of generating currents. We don't want to push bars along a set of rails through a magnetic field. It was a great way to introduce you to the topic so you could see why the charges move. But in real life, we're going to do different things. First thing I want you to realize is it doesn't matter if you move the wires or if you move the magnetic field. So in this case, I'm going to keep the wires stationary, this coil of wires. I'm going to drop a magnet through it. And you can see the moving magnet also created a voltage in my coils. Let's watch it again. So you'll see nothing happening on our graph. We drop this thing through and we see our spike of current as it falls through the coils. Here we have our coils hooked up to a little voltmeter, and you'll notice that when I put the magnet into the coils, when it went in, it created a voltage, and when I pulled it out, it created a voltage in the other direction. You'll also notice that when it was stationary, it did not create any voltage at all. So again, motion is key here to producing our electricity. My mechanical energy of moving the magnet generated electrical energy inside this coil. This idea can be used to take mechanical energy and turn it into electrical energy. So we learned how speakers took electricity and created motion of the cone, which then produced sound waves. These sound waves could then hit another cone, which will then mechanically move the coil and generate an electrical output. This reverse speaker is called a microphone, and it is our first example of induction. We are turning mechanical energy, sound energy, into mechanical energy into electrical energy using induction. And probably the most important one is a reverse motor. This is going to be the key to a lot of our electricity generation that we have today. So in our motor, we put electricity in and it caused this thing to spin. Mechanical energy came out. With our reverse motor, we are going to physically spin this coil. We're not putting any electricity in, we're putting mechanical energy in. And this spinning coil near a magnetic field will generate an electrical current. Just like we saw a few moments ago when I moved the magnet and I created electricity, now we're going to move the coils near a magnetic field and we're going to create electricity. This is called a generator or alternator. And this is going to be a key component in our modern life for turning mechanical energy into the electricity that we use to power our homes. We're going to do another lab where we dive into exactly what we have to do to get electricity to flow through a coil of wires. And it's going to lead to the most important thing of this entire unit. So that is where we are going. We now understand how magnetism, specifically changing or moving magnetism, can create electricity. Now we're going to dive in and find some mathematical relationships to help us predict how powerful our generators can be.